Hey, this is Dr. Poe. I want to give you just a really brief overview on buffers. So if you've heard the term buffer before, like what's a buffered solution, the textbook kind of definition is that it resists changes in pH. So pH we know is based on the concentration of protons in solution, those H plus ions. And so what does it mean to resist a change? It means that pH stays the same. And that is absolutely essential for lots of different experiments. It's also really important in your body. The pH range for your blood needs to stay between 7.35 and 7.45. And how do we achieve that really narrow range? You see here it's different by only 0.1. We do that with buffers. Okay, so what is a buffer? That is a weak acid and its conjugate base, or a weak base and its conjugate acid. And the reason for that is because if a little bit of base gets added in, the acid can neutralize that and become the base. And if a little bit of base gets added in, then if the little bit of acid gets added in, the weak base can take care of it. So either the conjugate base or the weak base can. And so understanding the components of buffers and kind of looking at these definitions, the trick is the two components of the buffer are going to be different by exactly 1 H. Well, actually, an H plus, because the acids donate an H plus and the bases pick up an H plus. So depending on what's added in, both of those components are there. If they need to donate an H plus, they can. If they need to pick up an extra H plus, they can, to maintain that same pH in a very narrow range. Okay, so just as a quick refresher, the acids and bases are always on the reactant side. The conjugate acids and the conjugate bases are always on the product side. So we can write this as, just so you can visualize, HA and B, right? So the conjugate acid is not what the acid becomes, it's what the base becomes. Because what's going to happen, oops, how do I change my color? Well, that stinks, whatever. So the acid is the proton donor, that H is going to go to the B, to the base. So we're going to end up with HB, and after this H plus is left, after a plus leaves, you're left with a minus. So we're going to have A minus. So this acid becomes the conjugate base, and the base becomes the conjugate acid. And as you can see, in each one of these cases, the acid and the conjugate base, the base and the conjugate acid, they're all different by exactly 1 H. The acid gave up the H, the base gained an H. They are different by 1 H plus in each case. So let's go ahead and do some examples so we can predict our buffer components, because we know that this acid, if we combine it with that conjugate base in a solution, like we have powdered forms of both of these, and we put both of these two in a solution, then we're going to have a buffer. Similarly, if we had a weak base that doesn't fully ionize and a conjugate acid and its conjugate acid, we can make a buffer out of those two components. Okay, so it's really important to note that strong bases, strong acids cannot do this. You cannot use that for buffers. So what are some examples of strong acids? HCl, HNO3, the first H of H2SO4. Let me think of a couple others. Maybe those guys are my favorite. I know HF is weak. There's not very many strong strong acids. Everything else is weak. There's some. HBr, HI, HClO3. That's chloric acid, perchloric acid, HClO4, because we got those polyatomic ions there. Yeah, I think that's pretty much everybody. You're going to notice that, like there's Cl, there's Br, and there's I. Those are group 8 elements, but what we're not going to see on here is HF. That's because HF is weak. And any acid that's not on here is weak, so that's including things that we know about, like citric acid is weak, acetic acid is weak. Those names that you've heard somewhere else. Anything that's not one of these 1, 2, 3, 4, 5, 6, 7 things is definitely weak. And strong bases cannot do this. Strong bases are not involved in buffers. And those are our metal hydroxides. Any other base is weak. So like ammonia's weak. Oh geez, there's tons of more weak ones. Let me find some examples. Ammonia's weak. Calcium carbonate that you find in Tums is weak. Calcium hypochlorite, methylamine, trimethylamines. Those are all weak. So if you see that OH, you know that it's strong. It's not going to form a buffer. Okay, so now let's talk about stuff that would form a buffer. How do we predict buffer components? First up, got to make sure it's weak. So if you memorize the strong ones, anything else is weak. There's way more weak ones than strong ones. So just memorize the strong ones. And so let's do, CH3, CH2, NH2 as an example. Okay, so number 1, is this weak? Yes, it is. Number 2, is it an acid or a base? Because this reminds us of ammonia, which we know is a base. This is probably going to be a base, and bases pick up protons from the acid donors. NH3, and then it's going to get a plus. So if we add an H plus into there, these are the two components that would be a buffer, and they're different by exactly 1 H. HF. We know this is an acid because there's an H on the left, and this would be hydrofluoric acid. It looks like hydrochloric or hydrobromic or all of those. So if we needed to predict the buffer component of that, it would be the conjugate base. So what does this look like after that H is gone? It looks like an F minus when that H is gone. It's different by exactly 1 H. Let's flip it around and do F minus. So F minus we know is a base. It has no H's on it. It would need to pick up an H plus, and when it did that, that plus would neutralize that minus, and we'd end up with HF. Let's think about some other things we can add. How about let's do HO, oops, I wrote that wrong. HO, I think I just wrote it wrong again. Oh yeah, I'm good. HOCl, no, I'm good. HOCl, we can tell this is an acid because there's an H on the left. So this is going to lose that when it makes a buffer. And the H plus will go somewhere else. So these two components. So that's how you really kind of can predict the buffer components. They're going to be different by 1 H. For the bases, those gain an H. Acids lose H plus. Okay. And so I think that's all I've got on that. There's probably additional practice problems out there. Good luck, guys.